The night of July 24th, 1943, radar station Hmelball on the northern edge of Hamburg, Germany. Oberreiter Klaus Hoffmann adjusted the brightness knob on his Würzburg radar display, the familiar green glow spreading across the cathode ray tube. 23 years old, 8 months of training at the Luftwaffe Signal School in Halle, and now 11 months spent tracking RAF bomber streams. He knew their patterns almost instinctively. The steady blips, the synchronized dance with flak batteries, the routine coordination with night fighter crews. After approximately 145 words, the rhythm of war on a radar screen had become second nature to him. If you're enjoying this deep dive into the story, hit the subscribe button and tell us in the comments where in the world you're watching from today. At exactly 57 minutes past midnight on July 25th, the Freya early warning radar picked up the incoming bomber stream, 113 kilometers out, bearing north-northwest. Hoffmann's hands moved automatically over his controls. This was the drill. Track the incoming formations, align the searchlights. Vector the Messerschmitt 110 night fighters toward their prey. Fight and win the nightly struggle for Germany's second-largest city. But tonight was different. At 23 minutes past 1 in the morning, as the first wave crossed into his sector, Hoffmann's screen exploded in light. Not with the crisp, readable echoes of aircraft he could interpret like a second language, but with thousands upon thousands of reflections. His display became a blinding sheet of illumination. Every direction, every range, every altitude, the neatly ordered grid of defensive zones dissolved into pure electronic chaos. His hands froze on the controls. In the underground operations room behind him, 3 other operators were staring at identical screens, flooded with the same impossible clutter. Lieutenant Dietrich, the watch commander, stood rigidly behind them, speechless as he watched the displays. For 8 long seconds, no one uttered a word. The backbone of Germany's night defense network had gone utterly blind in an instant. What Hoffmann couldn't yet understand, what none of the 200 radar operators across Hamburg's defensive system could grasp, was that this wasn't equipment failure. It wasn't a weather anomaly. It was a weapon. A countermeasure so deceptively simple, so brilliantly effective, that British scientists had hesitated for more than a year before unleashing it. And now it had turned billions of Reichsmarks worth of radar infrastructure into dead weight. 2 years of confidence built on successful interceptions were about to crumble beneath drifting clouds of aluminum foil falling slowly through the night sky. To understand what unfolded in that radar station north of Hamburg, one must first understand what German air defense had become by the summer of 1943. The network was known as the Kammhuber Line, named after General Joseph Kammhuber, commander of the Reich's night fighter forces since August 1940. It was, by any standard, one of the most advanced air defense networks ever built. The Kammhuber Line stretched from Denmark down through northern Germany and the Netherlands, then into Belgium and northern France. A chain of overlapping radar zones, each roughly 32 kilometers from north to south and 20 kilometers wide. The British referred to these defensive sectors as boxes. The Germans called them Himmelbett zones, 4-poster bed zones, because of their rectangular layout on the operations maps. Each Himmelbett zone held a tightly coordinated array of equipment. First came the Freya early warning radar, with a maximum detection range of 160 kilometers. Named after the Norse goddess, Freya operated at a wavelength of about 2.5 meters, with a pulse width of 3 microseconds and a peak output of 15 to 20 kilowatts. It could spot incoming bomber formations from far off, though it lacked accurate altitude measurement. Once Freya found a target and estimated its position, the zone's 2 Würzburg tracking radars took control. The Würzburg was the backbone of German radar capability. Operating at a 53-centimeter wavelength in the ultra-high frequency band, it used a 3-meter parabolic dish that could fold for transport. In service since May 1940, it had grown to nearly 4,000 units of various types by July 1943. Its accuracy was remarkable for its era. Range accuracy within 25 meters, angular accuracy of roughly 0.1 to 0.2 degrees. With that level of precision, ground controllers could direct night fighters to within visual distance of an enemy bomber. even on moonless nights. One Würzburg locked onto the incoming bomber, the second locked onto the assigned night fighter. A ground controller, reading both plots side by side, would relay exact steering commands to the pilot. Hamburg, Germany's second largest city and its most vital port, was guarded by 15 separate Himmelbett zones. 9 night fighter airfields operated around the area. 56 heavy anti-aircraft batteries and 36 light flak batteries formed a protective ring around the city. The searchlight units controlled hundreds of beams, many of them guided by radar. The entire system represented billions of Reichsmarks, thousands of trained specialists, and 2 years of evolving tactics. And the men who ran it had been taught, thoroughly and repeatedly, to trust in its power. Radar schools like the one at Halle took in raw recruits and turned them into technicians who could read the glowing traces on their screens as easily as a navigator reads charts. They learned to tell single aircraft from tight formations. They learned how to adjust for atmospheric distortions, ground clutter, and the many strange forms of interference nature could create. Most of all, they learned to trust their instruments. The Würzburg had earned that trust in combat. Obergreiter Klaus Hoffmann had been born in Bremen. In April 1920, his father worked as a machinist at the Focke-Wulf aircraft factory. His technical aptitude scores were high enough to qualify him for specialized training, and in January 1940, he was sent to the Luftwaffe Signal School at Halle and Dessau. The radar operator course lasted 8 months. Mathematics of wave propagation, the physics of radio frequency energy, and core electronics. Students trained on actual Freya and Würzburg units, learning to interpret cathode ray tube traces until pattern recognition became instinctive. By July 1943, Hoffmann had logged more than 700 hours tracking aircraft in live operations. He knew the signature shapes of different bomber types. Lancasters gave slightly different echoes than Halifaxes, and the larger Stirlings stood out distinctly. The Würzburg station at Hummelball was designated Radar Position Hamburg Nordwehr. On the night of July 24th, Hoffmann's crew consisted of 4 men. Their shift began at 2200 hours. At 00:30, the Freya network reported the main bomber stream approaching. Range, 90 kilometers. Direction, Hamburg. Estimated arrival, 01:15. Moments later, his display captured its first return, range 47 kilometers, a single aircraft flying straight and level. Hoffmann centered his tracking gate on the blip. A perfect lock. At 00:23, the impossible struck. His screen didn't brighten gradually. It didn't show a slow buildup of targets. It erupted. Instant, blinding saturation. 30 seconds before, he had seen a single clean return at 36 kilometers. Now the display was packed with what looked like hundreds, perhaps thousands of individual echoes. Every range band from 10 kilometers out to maximum detection distance lit up. Every bearing. The circular display that had been a precise tactical instrument only moments earlier had become a storm of overlapping signals. Hoffmann's first instinct was equipment failure. Perhaps the transmitter had failed, feeding noise into the receiver and producing false returns. But the pattern was wrong for a transmitter fault. These weren't random noise artifacts. These were distinct individual echoes. Each echo on Hoffmann's screen carried the unmistakable fingerprint of a genuine radar return. Every blip represented energy that had left his antenna, struck something metallic, and come back to his receiver. He scanned his indicators. Transmitter power, nominal. No fault lights. The Würzburg was functioning perfectly. This was no equipment malfunction. His next thought was atmospheric interference. Severe weather could produce false echoes, but the sky tonight was clear. No rain, no storms. The Freya operators had reported ideal conditions, and atmospheric clutter never looked like this. Those returns were diffuse and hazy. These were sharp, precise, like aircraft. Behind him, Lieutenant Dietrich was on the phone with zone headquarters, his voice carrying a tension Hoffmann had never heard before. "Sir, our display is saturated with contacts, all ranges, all bearings. We cannot distinguish individual aircraft. Request instructions." Through the RT operator's headset, Hauptmann Weber's voice blasted loud enough for Hoffmann to hear. "Jäger Nordwehr, what is my vector? I have no target on my Liechtenstein. Repeat, No airborne radar contact. Where is my target? The RT operator turned to Dietrich. Dietrich stared at Hoffman's screen. Hoffman stared back at the impossible storm of returns. For 10 long seconds, the only sounds in the operations room were the steady hum of the machinery and the faint crackle of the field radio. Then the reports began to pour in from across the defensive grid. Hamburg Nordein's display saturated. Hamburg Nord 2 cannot track individual targets. Hamburg West-Drei radar returns covering entire display. Hamburg Ostwehr unable to vector fighters. One after another, every Würzburg station around Hamburg reported the same catastrophe. The entire defensive network had gone blind at the same moment. At zone headquarters, the watch officer made a decision that would ripple through Luftwaffe command all the way to Berlin. He ordered the night fighters to return to base. Without radar control, incapable of tracking the bomber stream or guiding interceptions, the Mi-110s were effectively flying blind. They would land, refuel, and wait for the mystery to resolve. The searchlight units, with their radar-directed master beams now sweeping uselessly through empty air, switched to manual control. Teams of 3 took over each light, one scanning the sky with binoculars, 2 others swinging the beam wherever he shouted. It was a crude system dragged forward from 1918. The precision of 1943 had vanished. The flak batteries began firing box barrages, walls of bursting shells at fixed altitudes and coordinates, hoping something in the darkness would fly into them. Without radar to track individual aircraft, the flak crews could do nothing more than fill sections of sky with shrapnel and hope a bomber crossed their line of fire. The precision they had developed over 2 years of radar-directed shooting was gone. They were firing at phantoms. Above Hamburg, 791 RAF bombers moved through defenses that, under normal conditions, would have destroyed 50 or 60 of them. The few night fighters that managed to make visual contact found themselves alone in a sky crowded with bombers, unable to coordinate with ground control, unable to receive vectors toward new targets. The Himmelbett system, which had once brought down hundreds of RAF aircraft, had simply stopped working. In the Himmelball radar station, Hoffman kept watching his display. The saturation of returns hadn't lessened. If anything, it had grown thicker. New contacts flickered into existence constantly. The entire defense grid remained blind, and no one could explain why. At Orowator 7, 24 minutes after the first wave of saturation, something shifted. The southernmost edge of the mass of contacts began to thin. Slowly, over 3 minutes, the returns on the lower portion of Hoffman's display weakened. The solid wall of light broke into scattered dots, then fewer dots, then nothing. For a moment, Hoffman thought the malfunction had cleared. Then it struck him. The bomber stream had passed through his sector. Those overwhelming returns had been real aircraft, hidden behind something that created thousands of false echoes. The bombers were now directly over Hamburg, dropping their ordnance, and he had been powerless to stop any of them. For 90 minutes, from 0100 to 0230, Hamburg burned. Even deep underground, Hoffman heard the detonations. The building overhead shook with each blast. Dust drifted down from the concrete ceiling like ash. At Aero 315, the last bombers exited Hamburg's airspace. Hoffman's display cleared completely. The false echoes vanished as abruptly as they had appeared. His Würzburg functioned perfectly again. The transmitter held steady at its normal output. The receiver was crisp and sensitive. The screen showed clean, empty sky. Whatever had blinded German radar had stopped the moment the bombers left. At 0430, Lieutenant Dietrich received fresh orders from zone headquarters. All radar crews were to search the ground beneath the bomber routes, look for anything unusual, collect anything that might have caused interference. Report immediately. At 600, as dawn broke over Hamburg, Gefreiter Schneider returned from his patrol. He carried a small cardboard box. Inside it were narrow strips of aluminum foil attached to black paper. Each strip measured roughly 27 centimeters long and 2 centimeters wide. Schneider had found hundreds of them scattered across half a kilometer, dangling from trees, lying in open fields, covering rooftops and roads like metallic snow. Hoffman lifted one of the strips toward the weak morning light, creeping into the entrance of the underground bunker. The aluminum caught the sunlight and flashed. It weighed almost nothing, just a sliver of foil. yet it was anything but random. He understood immediately. The length of the strip matched roughly half the wavelength of the Würzburg radar's operating frequency, an ideal dipole antenna. When a radar pulse struck it, the strip would resonate perfectly, reflecting a powerful return. On a radar screen, each one of these flimsy pieces would appear indistinguishable from an aircraft. 7,000 bundles had been dropped, each containing 2,200 strips, released from 791 bombers at one bundle per minute. 15 million pieces of foil, 15 million radar echoes. It was genius in its simplicity and devastating in its impact. By mid-morning, intelligence officers from Luftwaffe High Command arrived. They photographed every strip, measured them, analyzed them, and confirmed precisely what Hoffmann had already concluded. The British had engineered these foil strips specifically to defeat the Würzburg system. They knew its operating frequency. They understood its vulnerabilities, and they had crafted a countermeasure that cost almost nothing, yet nullified an air defense network built at staggering expense. General Josef Kammhuber, commander of Germany's night fighter forces, would later admit during post-war interrogation, the whole defense was blinded in one stroke. It was no exaggeration. In a single night, the Kammhuber line, the complex, meticulously designed defensive system stretching from Denmark to France, had been rendered obsolete by thin strips of aluminum foil. By 0800 hours on July 25th, the numbers began arriving at zone headquarters. Of the 791 RAF bombers that struck Hamburg, only 12 had been lost, a mere 1.5% loss rate. Under normal conditions, the city's defenses would have downed 40 to 50 aircraft, a 5 to 7% attrition rate. The difference meant 350 to 400 British airmen survived simply because German radar had gone blind. The devastation on the ground was immense. Approximately 16,000 buildings were destroyed, 3,000 civilians were killed, 120,000 left homeless. The Blohm and Voss shipyard was severely damaged. The Kluckner aero engine plant was hit. Several U-boats under construction were obliterated. Hamburg's electrical grid had taken heavy damage, and this had been only the first night. The British would return, they would drop the aluminum strips again, and German radar operators would sit before their scopes watching the same impossible saturation. Unable to track targets, unable to vector fighters, unable to defend their own airspace. Hoffmann stood at the entrance of radar station Humboldt-Tal as dawn broke over Hamburg. Smoke columns coiled upward from dozens of fires across the city. The sky, which should have been blue, had turned a dense, ashen gray. From his position north of the city, he could see shattered rooftops and collapsed buildings. He still held one of the aluminum strips between his fingers. 8 months of training, 700 hours on operational duty, 2 years of successful interceptions and tactical victories, all of it nullified by a weightless sliver of metal foil. In the days that followed, the scale of the catastrophe became undeniable. RAF Bomber Command returned on the night of July 27th, 777 aircraft, window deployed again, German radar blinded again. This time, conditions in Hamburg produced a firestorm. Temperatures surged to 800 °C. Winds roared at 240 km/h. Approximately 20,000 people died in a single night. It became the deadliest bombing raid in Europe to that point. The Luftwaffe responded with desperation. Oberst Hajo Hermann developed a tactic called Wild Sau, wild boar. Single-seat day fighters would patrol over burning cities and attack bombers visually, using the flames below as illumination. It was crude, it was dangerous, and it represented the total abandonment of the radar-directed precision that had once defined German air defense. Engineers at Telefunken began emergency work on new countermeasures, systems with names like Wurzlaus and Tamlaufs, modifications meant to separate real aircraft from window echoes by analyzing subtle signal variations. But their development would take months. In the meantime, radar operators stared at screens they could no longer trust. By August 1943, mere weeks after the Hamburg raids, 45% of all German fighter aircraft had been pulled from frontline combat and reassigned to home defense. The strategic air offensive was forcing Germany to divert resources from the Eastern Front, from the Mediterranean, from every theater where the Luftwaffe operated. The shift in industrial production was just as dramatic. Factories originally meant to sustain Germany's offensive war machine were now being redirected to defend the Reich's own cities. It was one of the many unintended consequences of Operation Gomorrah. Albert Speer, Minister of Armaments and War Production, would later tell Allied interrogators, "It was quite a surprise to us when the first Hamburg raid took place because you used some new device which was preventing the anti-aircraft guns from finding your bombers. So you had a great success." I said then, in a meeting of the Air Ministry, that if you would repeat this success on 4 or 5 other German towns, we would collapse. They did not collapse, but they never recovered their confidence either, and what emerged after the war made that loss of confidence even more bitter. German scientists had known about this countermeasure since 1940. They had developed their own version called Duppel. They had tested it, they had confirmed it would blind enemy radar, and they had deliberately chosen not to use it because they feared the British would copy it and use it against German cities. For more than a year, both sides possessed the same weapon. Both sides understood exactly how effective it would be, and both sides refused to employ it for the same reason, until July 24, 1943, when Air Chief Marshal Arthur Harris decided the time had come. The British deployed Window, and the Germans discovered in an instant that the British had embraced the very tactic their own high command had suppressed. The irony was unmistakable. 6 weeks after Hamburg, on the night of October 7th, 8th, the Luftwaffe finally dropped Duppel over London. German bombers attempted to revive the night raids, scattering radar jamming strips cut to 80 cm by 1.9 cm, precisely tuned to British radar frequencies. But by then, the strategic balance had shifted beyond repair. The Luftwaffe had too few bombers. The RAF had too many fighters. The so-called mini-blitz of Operation Steinbock from February to May 1944 achieved almost nothing. The technological advantage had moved on. The side with greater industry, greater resources, and greater adaptability would prevail. Germany had built a sophisticated defensive network on the assumption that their radar advantage was permanent. Britain had built a countermeasure so simple that any factory with aluminum and paper could produce it. Complexity had been defeated by simplicity. Oberfunker Klaus Hoffmann remained at radar station Humboldt-Bühl for another 8 months. He continued to operate his Würzburg. He watched his display fill with Window on every raid, relying on intuition and experience, techniques that were more art than science, to find real aircraft in the chaos. The precision of early 1943 never returned. The German engineering response came with remarkable speed, though the damage was already done. Within weeks of the Hamburg raids, Telefunken began work on modifications to the Würzburg system designed specifically to counter Window. The first of these was designated Würzlaus, a combination of Würzburg and Laus. The name was fitting. The new system was intended to pick the Window infestation out of the radar display. Würzlaus operated on the principle of Doppler shift. When radar energy reflects off a moving object, the frequency of the returning signal changes slightly. Aircraft traveling at 300 to 400 km per hour created a clear, measurable Doppler shift, while aluminum strips drifting slowly downward at barely 10 to 20 km produced almost no change at all. By adding circuits that compared the frequency of each transmitted pulse with the frequency of its returning echo, operators could, in theory, separate genuine bombers from falling chaff. To do this, engineers installed a stable oscillator that locked the transmitter's frequency, keeping the phase consistent between outgoing pulses. Additional filtering components examined the returned signals for Doppler patterns. The radar display was then altered to emphasize echoes that showed noticeable frequency shifts and to suppress those that did not. In theory, the Window would fade and real aircraft would appear clearly again. In practice, the system was difficult. The modification reduced the Würzburg's range by nearly 30%. The new circuitry was complicated and often unreliable. Only a small number of highly trained operators could use it properly. Even so, by November 1943, roughly 1,500 Würzburg units had been upgraded with either the Würzlaus system or an improved version called Tuslaus. It wasn't a complete solution, but it returned a portion of their lost capability. A second countermeasure, named Nuremberg, used a different method. Mechanical propeller modulators analyzed the patterns of reflected signals, helping distinguish chaotic returns from tumbling window strips and the steadier reflections from real aircraft with fixed structure and orientation. Again, the system demanded skill. Only a few operators mastered it, but those who did could see through chaff with reasonable success. German engineers also attacked the issue from the opposite direction. If existing radar bands were compromised, then completely new frequencies would be needed. The Würzburg's bandwidth expanded from its original 10 MHz range to more than 100 MHz. Multiple operating bands were introduced, and a modification known as Wismar, released in the summer of 1944, allowed operators to switch rapidly between frequencies. If the British cut window to jam one frequency, the operator could immediately move to another. For airborne radar, the answer was the Liechtenstein SN2. Earlier Liechtenstein B, C, and COM models functioned in the UHF range, leaving them vulnerable to chaff. The SN2 shifted to a lower frequency around 90 MHz in the VHF band. Window cut to counter, the Würzburg was the wrong length to affect the SN2, making it temporarily immune. But the SN2 introduced its own limitations. Its minimum detection range was initially 900 meters, far too long for effective night fighter interception. Aircraft needed to retain their old Liechtenstein sets alongside the new one, creating a forest of antenna arrays on fighter noses that reduced aircraft speed by up to 50 km/h. By early 1944, improved versions reduced the minimum range problem, allowing removal of the old equipment. But by then, the Allies had captured an intact SN2 when a Junkers 88 night fighter accidentally landed at an RAF base in July 1944. Within weeks, Allied jammers were targeting the SN2 specifically. It became a technological arms race with no finish line. Every German countermeasure prompted an Allied countermeasure. The British developed carpet jammers to blind Würzburg radars with broad-spectrum noise. The Germans modified Würzburg to operate on multiple frequencies. The British added frequency-agile jammers. The Germans developed centimetric radar. The British captured it and jammed it. The fundamental strategic balance had shifted. Germany, with its limited industrial capacity devoted increasingly to replacing losses, could not match the pace of Allied electronic warfare development. Every modification consumed resources. Every new radar system required factory time that could have gone to producing fighters or tanks. Every trained radar operator diverted to learning new countermeasure techniques was one less pilot, one less gunner, one less soldier at the front. For the men who operated German radar systems, the months following Hamburg brought a different kind of warfare. They sat at their displays knowing the technology they depended on could be rendered useless at any moment. The confidence that had defined their work disappeared. Every raid became an exercise in adaptation and improvisation. Oberreiter Klaus Hoffmann remained at Radar Station Hummel until April 1944. In those 9 months, he tracked hundreds of raids. Some nights, the modifications allowed him to see through the window, jamming and vector fighters successfully. Other nights, his screen became the same impossible mass of returns he had witnessed on July 24th. There was no consistency, no reliable procedure. Each raid was different. The psychological toll extended beyond individual operators. The entire German air defense system had been built on the premise of technological superiority. The Kammhuber line, the Himmelbett zones, the carefully coordinated network of radar stations and fighter bases. All of it assumed German radar would maintain its advantage. When that assumption proved false, the entire doctrinal structure became questionable. By August 1943, less than a month after Hamburg, 45% of all German fighter aircraft had been pulled from combat theaters and reassigned to homeland defense. Fighters desperately needed on the Eastern Front, in the Mediterranean, and in France were instead patrolling German cities. The strategic bomber offensive was achieving one of its primary objectives, forcing Germany to divert resources from offensive operations to defensive ones. The numbers tell the story with brutal clarity. In 1942, RAF Bomber Command flew approximately 48,000 sorties against German targets and lost about 7,600 aircraft, a loss rate of 3.3%. In the second half of 1943, after the introduction of window, Bomber Command flew approximately 60,000 sorties and lost around 1,500 aircraft, a loss rate of 2.5%. The offensive was intensifying while losses were decreasing. The reallocation of German industrial production had cascading effects. Anti-aircraft guns in Germany increased by 25% in the months following Hamburg. These guns required crews. By late in the war, anti-aircraft units employed hundreds of thousands of personnel and consumed 25% of all ammunition produced by German industry. Every anti-aircraft gun crew member was a person who could have been fighting at the front. Every shell fired at bombers was a shell not available for ground combat. The bombing campaign's effectiveness in destroying industrial capacity is debated by historians. Many factories were dispersed, production continued, and German fighter production actually increased in 1943 despite the raids. But the diversion of resources to air defense was undeniable. Germany was fighting a multi-front war with finite industrial capacity. Every ton of steel devoted to flak towers was steel not available for tanks. Every trained mechanic maintaining radar equipment was not maintaining vehicles in Russia. The psychological impact on German civilians was harder to quantify but equally significant. After Hamburg, approximately 1 million people evacuated the city. 60% of the housing stock was destroyed or damaged. The city's labor force was reduced by 10%. Other cities watched and understood they could be next. The sense of invulnerability that radar-directed defenses had provided evaporated. Albert Speer's statement to interrogators after the war remains chilling. He told Hitler's inner circle that 4 or 5 more attacks like Hamburg would lead to collapse. They did not collapse, but the fact that Germany's Minister for Armaments and War Production believed such an outcome possible reveals the psychological impact of that week in July 1943. For radar operators like Hoffman, the experience was more personal and immediate. He had been trained to believe his technology was superior. He had seen it work for 2 years. Then, in less than a minute, that superiority vanished. The equipment still functioned, the physics still applied, but the advantage was gone. And with it went the certainty that skill and training would be enough. The war had become unpredictable in new and unsettling ways. The British had more bombers, better countermeasures, and greater industrial capacity. German operators could adapt, improvise, and occasionally succeed, but they could no longer dominate. The night of July 24, 1943, marked a turning point that extended far beyond Hamburg. It demonstrated a principle that would define warfare for the remainder of the 20th century and into the 21st. Technological advantage is temporary, and the side with greater capacity to adapt will prevail. Window was not a sophisticated countermeasure. It was strips of aluminum foil. The physics were elementary. The manufacturing was trivial. What made it devastating was not complexity, but timing and scale. The British waited until they had overwhelming numbers of bombers, until the Luftwaffe's retaliatory capacity was diminished, until the strategic calculus favored deployment. Then they used it everywhere simultaneously. 15 million strips dropped over one city in one night. German radar operators had no time to adapt because the adaptation had to happen under the worst possible conditions during an actual attack. This established a pattern that continued throughout the war. The Germans would develop a countermeasure. The Allies would overwhelm it with numbers or develop a countermeasure. The Germans would introduce a new radar frequency. The Allies would capture it and jam it, back and forth month after month in an electronic warfare arms race, where the side with more resources eventually ground down the side with fewer. Oberreiter Klaus Hoffmann survived the war. Records show he was transferred from radar operations to General Luftwaffe ground duties in April 1944, possibly because his technical expertise was needed elsewhere as Germany's situation deteriorated. His ultimate fate is not recorded in available archives, but thousands of radar operators like him continued their work until the final days of the war, tracking raids they often could not stop, operating equipment that had lost its decisive edge. The Würzburg radar itself remained in service until the end of the war. Modified versions continued to provide some capability in the hands of skilled operators using countermeasure modifications. It could still track targets through jamming, but it never regained the dominance it had possessed before Hamburg. The 4,000 Würzburg systems Germany produced represented billions of Reichsmarks in investment and thousands of hours of training. Window rendered that investment partially obsolete for the cost of aluminum foil and paper. After the war, captured German radar equipment was studied extensively by Allied scientists. Several Würzburg systems were taken to Britain and the United States for analysis. Ironically, some were later used for scientific research, including early radio astronomy studies. The technology that had failed to stop the bombing campaign found peaceful applications in studying the cosmos. The broader lesson of Hamburg transcends the specific technology. It speaks to the nature of war in the modern age. Technical innovation matters, but industrial capacity, resource availability, and adaptability matter more. Germany produced excellent radar systems, skilled operators, and sophisticated defensive networks. But when faced with an opponent who could produce countermeasures faster than Germany could develop countermeasures, technical excellence was not enough. There is a profound irony in the mutual possession of chaff technology. For over a year, both sides had the weapon but feared to use it. Each assumed the other did not possess it. Each worried that deploying it would reveal its secrets to the enemy. In reality, both sides had independently developed the same solution to the same problem. The decision to deploy came down to strategic calculation, not technological discovery. The British had more bombers and less to lose. The Germans had fewer bombers and more to fear. So the British deployed first, and the Germans discovered they had been sitting on the same countermeasure all along. Oberreiter Klaus Hoffmann, staring at his saturated radar display on the night of July 24, 1943, witnessed the beginning of this transformation. He did not know the aluminum strips had a name. He did not know the British had feared using them for over a year. He only knew that his world, his training, his experience, his confident understanding of how the war was fought, had changed fundamentally in the space of seconds. The green glow of his cathode ray tube, once a window into the night sky that revealed every approaching threat, had become a blizzard of false echoes. And in that moment, as thousands of bombers passed overhead unimpeded by the defensive network that should have stopped them, the future of aerial warfare was written in aluminum and flame.